Welcome to chapter 24, where we're introducing electromagnetic waves. So it's not a very long chapter, and we don't have many formulas to actually remember. When we work with electromagnetic waves, and that includes a large category, that's visible light, that's electricity, that's microwaves, that's ultraviolet radiation, infrared radiation. It's just a big category. When we work with these waves, we have a group of equations called Maxwell's equations that we discuss. Now, James Clerk Maxwell was famous for being able to reconcile that electric and magnetic phenomena could be described mathematically. And he came up with his 4 equations. It's enough for you to realize that there are 4 equations, that they're called Maxwell's equations, and they mathematically explain things that we've talked about. The first one is a mathematical representation of Coulomb's law. Remember, Coulomb's law was the forces associated with electric charges. And in this one, they're showing that the charges, that's the Q, and the surface, that's the ds. If you integrate over the entire surface, that's what this funny little symbol means. The electric field over the entire surface actually has to add up to the net charge on the surface. If you look at his second equation, it describes the fact that we know that magnetic field lines are continuous, that we don't have magnetic monopoles, that there's not an isolated north magnetic pole without a south pole to go with it. The third equation talks about the electric field being produced by a changing magnetic field. So it's a mathematical representation of Faraday's law. And you can see phi, how the magnetic flux changes over time is equal to the electric field integrated over a specific region. And then the last equation is that the magnetic field is produced by an electric current or by a changing electric field. And you can see it's this horrible little equation. The nice thing about these equations is you're not going to have to memorize them. I just wanted you to be aware of their existence. So changing electric fields produce changing magnetic fields. We talked about this in the previous couple of chapters, and how, you know, if you vary the position of a wire with respect to an outside magnet, you can induce a current in the wire. Well, the reverse is true. Changing currents can produce changing magnetic fields. So as the electric field varies, the magnetic field varies over time. So the result is going to be that you can propagate or send electromagnetic waves through space when you have a conductor connected to an alternating power supply, so an AC power supply. Because both the electric and the magnetic fields oscillate, you can represent your electromagnetic wave as being composed of these E and B fields in phase with each other and at right angles to each other, and at right angles to the direction of propagation. We have a little diagram that shows this. So the blue wave is the electric field variation, and the pink one is the magnetic field variation. And you can see that the blue plane and the pink one are at 90 degrees to each other. You can see that a crest lines up with a crest, and a zero lines up with a zero. So they're in phase. They're at 90 degrees. We can see that by the directions of the planes. And the direction of propagation would be along this axis. So in general, we say that accelerating electric charges produce electromagnetic waves. Maxwell is famous for calculating the speed of the electromagnetic wave to be 3 × 10⁸ meters per second. That's the same as the speed of light. We'll talk about this value again in later chapters. So let's talk a little bit about light. Light is a form of electromagnetic radiation. It's got both a wave and a particle nature. Sometimes we talk about this as being the dual nature of light. The wave part of it is described as acting like a transverse wave. You may remember that water waves are transverse waves. A sine wave is a transverse wave. So a transverse wave, it goes up, it comes down, it goes up, it comes down. The vibration is in the vertical direction in the one I've drawn, but the wave propagation is horizontal across the page. So for a transverse wave, vibration and propagation are at 90 degrees to each other, and it looks like a sine wave. So we've already said that light is composed of electric and magnetic fields in phase with each other and at right angles to each other. We can describe light as acting like a wave. Remember, these are just descriptions. They help us to understand natural phenomena. So Maxwell was the one that predicted that the electromagnetic radiation would travel at 3 times 10 to the 8th meters per second. You remember just a few minutes ago, we talked about that. And that is the same as the speed of light. It took Heinrich Hertz in 1887 to actually measure the speed of electromagnetic radiation and experimentally prove that Maxwell was correct. So the conclusion that we can draw from all of this is that light is a form of electromagnetic radiation. So what are some of the properties of electromagnetic waves? Well, we need to look at those. They travel with the speed of light. So electromagnetic waves travel at 3 times 10 to the 8th meters per second. They are transverse waves with the E and B fields at right angles to each other. And the ratio of E to B, if you have the value of the electric field and divide it by the value of the magnetic field, you will get little c, which is the speed of light in a vacuum. This is not supposed to be a capital C. This is supposed to be a lowercase c. And you can see it's just bigger than we're accustomed to. So this is supposed to be little c. Little c is what we use to symbolize the speed of light in a vacuum. All right, 3 times 10 to the 8th meters per second. Electromagnetic waves carry both energy and momentum, which they can deliver to a surface. Now, that is something that should be a little puzzling, but if you think about it, actually makes a little bit of sense. So when sunlight hits the surface, sunlight is a form of electromagnetic radiation, and it delivers energy to the surface. If you put your hand out in the sun, eventually it will warm up. So energy is being transferred. The momentum part is probably a little harder to understand. When the electromagnetic radiation hits the surface on a molecular level, you have momentum being transferred. Remember, transfer of momentum is like in a car crash or two pool balls hitting each other, that the mass and the velocity of one object when it slams into another object will change the velocity of that second object. So when electromagnetic radiation strikes the surface, it changes the velocity of the molecules in the surface. So we can describe electromagnetic radiation in terms of these waves. If we do that, then we have to look at some of the properties. We have to look at the wavelength. Wavelength is the distance between two like points on a wave. So it could be crest to crest or trough to trough. It is symbolized by the Greek letter lambda. Here's lambda, it's a lowercase Greek letter. It looks like an upside down Y, if you will. Normally, the taller line is at an angle, sort of tilted left, And the short line then comes down about halfway. So Greek letter lambda, the horizontal distance between two adjacent crests or troughs are measured in angstroms. Angstroms are abbreviated. It's not supposed to be a capital A. It's supposed to be this symbol, an A with a little circle over the top. So this abbreviation is incorrect. It's an A with a little circle over the top. 1 angstrom. Let's just get rid of this. Maybe that'll make it look more correct. Where 1 angstrom is equal to 1 times 10 to the minus 10 meters. So an angstrom's really small, which is the same as 1 times 10 to the minus 8 centimeters, or in nanometers, 1 nanometer is 1 times 10 to the minus 9 meters. Now you do need to know this equation, C equals lambda F. These are all lowercase letters, lowercase c, lowercase lambda, lowercase f. C is the speed of light in a vacuum, so 3 times 10 to the 8th meters per second. Lambda is the wavelength measured in meters, and f is the frequency measured in hertz or cycles per second. Visible light, the light you and I see, ranges from reds to violet. So at the red end of the spectrum, the wavelength would be 7,500 angstroms or 750 nanometers. And at the violet end, it would be 4,000 angstroms. Again, these symbols are incorrect. I need to change them. It should be with a little circle over the A. Or 400 nanometers for the violet end of things, for the lavender end. So an increase in wavelength, if lambda goes up, F comes down, and vice versa. If wavelength goes up, frequency comes down. So things with a large wavelength have a small frequency and vice versa. So let's look at some things in the electromagnetic spectrum. This is a graphic from I thought it was from your book. It is. Let's look at our little graphic on the electromagnetic spectrum. So radio waves have a wavelength of about 10 to the third or 1,000. Microwaves are 10 to the minus 2. Infrared radiation, 10 to the minus 5, and so on. Gamma rays, 10 to the minus 12 meters. So you can see it runs the gamut from really large wavelengths to really small ones. Frequencies, all the way from a low of 10 to the 4th, all the way to a high of 10 to the 20th. And temperatures of bodies that emit radiation in these wavelengths, you can see go from relatively cool to very, very hot. I like the fact that the author of the graphic gave you physical things to compare it with and talks about whether it can penetrate the Earth's atmosphere or not. So radio waves obviously do. Microwaves do not. Visible light does, and so on. All right, let's look at some of these in a little detail. So radio waves, this is like if you turn on the radio in your car and you listen to it. AM radio has frequencies in the neighborhood of 10 to the 6th hertz. FM radio has frequencies in 10 to the 8th hertz, but they all fall between 10 to the 2nd hertz and 10 to the 8th hertz. So that's the range. Radio waves can be used to actually perform surgery, surprisingly enough, when excessive bleeding is a problem. So you send in electromagnetic radiation in the radio wave frequency, and you're able to disrupt the molecules without the same kind of trauma associated with, say, a scalpel. TV signals overlap with the high frequency end of radio waves and the low frequency end of microwaves. Microwaves are 10 to the 8th hertz to 10 to the 12th hertz. This is a portion of the spectrum that includes radar, and cell phones are transmitted at this range. Microwaves, well, I use my microwave every day to cook something. What's really cool about microwaves is that in your home, the microwave oven is designed to oscillate the hydrogen atoms in food and make them vibrate very quickly. So this rapid vibration ends up creating heat energy, and then you get cooking. Infrared I'm sorry, one more thing about microwaves, because we have a limited range that we transmit under. As you add more and more cell phones out there, you have to come up with better ways to transmit. And when they first started out, you could be talking on a cell phone, and sometimes you got someone else's conversation. It was really weird in the very beginning. They've gotten much better at it. Infrared radiation. Infrared radiation, if you have a hot object, it gives off infrared radiation. All objects emit some infrared radiation, but the hotter the object, the more it emits. Night vision goggles detecting the infrared. So a live person is going to emit a different amount of infrared radiation than the soil around them. It comes in handy sometimes. Visible radiation, so that's the part of the spectrum that we can see in, and we've already talked about how they go from 400 nanometers to 750 nanometers. And again, an angstrom is 10 to the minus 10th meters. Let's talk about the ultraviolet and the other two ranges. So ultraviolet radiation, this is a radiation that gives you skin cancer and a tan. Most ultraviolet radiation doesn't pass through glass. We're lucky the ozone layer surrounding the Earth actually converts ultraviolet radiation into infrared radiation, so we are somewhat protected. Ultraviolet radiation is also used to kill germs. Maybe in high school, you had to share goggles in chemistry with other students, but they were kept in a cabinet. That cabinet probably had a UV light, an ultraviolet light in it, and it was used to disinfect the goggles. During the COVID epidemic, one of the popular items out there has been the selling of UV lights to kill the COVID virus on different surfaces. X-rays. So X-rays are produced when high energy electrons slow down after striking a metal target. We use them in medicine. Obviously, you have dental X-rays. If you've ever suspected that you've broken a bone or had a bad chest cough, you maybe have had an X-ray there. Most people can't, well, we've all probably had dental X-rays, but then X-rays of bones, probably you can't get to be 20 without having one X-ray or another. Gamma, well, I'm sorry, one more thing to mention about X-rays is we don't consider there to be a safe level of exposure. All exposure to X-rays is considered to do some molecular damage, but you weigh the pros and cons. You weigh the benefit to the loss. And in the long run, they've gotten much better at using them and keeping us safe and only using the bare minimum. So X-rays are considered a very safe diagnostic tool. Gamma rays are very high frequency. They are emitted from radioactive nuclei, and we'll talk about this in a later chapter. They are used in medicine, and they're also used in the food industry, surprisingly enough, to kill germs and bacteria. And again, we'll come back to them in a later chapter. I think it's chapter 31. So let's talk about how we measure. Whoops, I overshot. I got carried away. Let's talk about measuring the speed of light. So one of the things in physics we have spent a lot of time on is measuring the speed of light. People have been trying to do it for hundreds and hundreds of years. Galileo is famous for being the first person to actually design an experiment to actually physically measure the speed of light. His little experiment had two people separate from each other by about a couple of miles, and they had lanterns with shutters. So one person would stand on one mountaintop, one on the other, and the ideal was that one person would remove the shutter, and so the beam of light would go out. When the second person saw it, he was supposed to remove his shutter, the beam would go back, and because they knew how far apart they were, they would measure this time interval and be able to calculate the speed of light. The problem is that they didn't have a very accurate way to measure time back in the 1600s. And so the instant the first experimenter removed the shutter on his lamp, the second one removed the shutter on theirs, and the conclusion was that it was an instantaneous reaction, that light travels instantly from person A to person B. There was no discernible lag in time, but Galileo tried. If you look at Galileo's experiment and try to do the math, velocity is distance divided by time. So let's see what time interval he'd have to be able to calculate. If the distance is 2 miles and we want to convert that 2 miles to meters per mile, because we know the speed of light in meters per second. So 2 miles times the 1.6 times 10 to the 3 meters per mile, divided by 3 times 10 to the 8th meters per second, which is what we know the speed of light is. That means that the time he would have had to have been able to measure was 1.07 times 10 to the minus 5 seconds. I promise you, back in the 1600s, they didn't have a way to measure time intervals this small. So since then, since Galileo's time, there have been numerous people, and I will not mention them all. I've just picked 3 to come up with and discuss. So one was Romer. Romer was a Danish astronomer. You can see he lived right after Galileo. He was the first person to successfully measure the speed of light. He used astronomical techniques, and he looked at the differences in the periods of the orbits of Jupiter's moons. So when a moon passes in front of a planet, you can actually see it because it's a little dark spot migrating across the planet. So he was able to, by using this, calculate that light was traveling at 2 times 10 to the 8th meters per second. When you consider that the value we use is 3 times 10 to the 8th meters per second, he only had a 33% error, and that's not bad when you think about what he had available to use. Albert Michelson was an American who was famous for spending about 40 years doing research on the speed of light. Michelson looked at what other researchers had used and came up with sort of a hybrid model of theirs. He looked at Galileo with the big distances, but then there was a French researcher named PHY who used a toothed wheel, and what it did is it made the light flash as it would spin, because the light could only penetrate where the openings were in his toothed wheel. And by knowing how fast the wheel would spin, he could figure out the speed of light. So what Galileo did is he sort of refined PHY's technique and Galileo's technique to come up with something that worked fairly well. Michelson used an 8-sided mirror, an octagonal mirror, and it would rotate, it spins. He had a light source. The light would hit one face of the mirror, bounce off, and hit a fixed mirror 22 miles away, bounce back and hit another of those flat places on the mirror, and an observer would be able to say, aha, I see the light. The only time your observer can see the light is when the mirror is exactly in the right position. So it would be every 1/8 of a rotation that your observer was able to detect the light. by having the 22-mile distance, over 10 times farther away than Galileo was able to use, and by having better ways of measuring time, distance, and speeds of rotation, Michelson was able to come up with a much more accurate value. As I said earlier, you could only see the light every 1/8 of a rotation. So again, velocity is distance divided by time. And if we look at this, the time would be 1/8 times 1 divided by the frequency of our rotation. So we can calculate the speed of light as 8 times the frequency that the mirror rotates at times the distance the light has to travel. If you used a 6-sided mirror instead of 8 in the equation, there'd be a 6 in the equation. So what we've come up with for the speed of light is this value. For us, we're going to round it off to 3 times 10 to the 8th meters per second. I don't know what happened to my slash seconds over here. Slash second, it somehow got omitted. All right, so we're going to use that in our calculations. We will stop the share and stop the recording.